To summarize, we could classify the routing into two classes. First is based on their static or a dynamic nature. In a static routing, routes are usually manually established, and this is okay for a small network. When you get a larger network, establishing manual routes or static routes become a very hard task, so people use dynamic routing. In a dynamic routing, your routes can be periodically updated, for example, in a response for a cost change in a link. For example, one link is becoming congested, or one of the cables, for example, get cut, or any other disturbance in that link. Or if you added one new router or so on. On the other hand, you could classify the routing algorithm according to the knowledge of the router. We saw there are three levels of knowledge. The first is isolated. It's not really used in practice, but the most common ones are the decentralized and the global. In the decentralized, the router has some limited knowledge on about the network. It doesn't have the full knowledge of the network. It uses an iterative process to reach this destination. We will look at the distance vector algorithms in more details in this part of the video that enables the decentralized algorithms. On the other hand, the global algorithms uses link state algorithms, which also we will look at them in more details in this video. We will start off with the link state algorithms, and remember this is part of the global algorithms. What does a global algorithm mean? Means every node has a full knowledge of the topology of the network. So each of these nodes, they shared exactly the same information, and they have the information of the entire network. So how is this really achieved? Each router broadcasts the link state, what it knows, and they share the information between these routers. We will see in details how the Dijkstra's algorithm works. This is a very famous algorithm that's not only used in networking, it's also used in GPS navigation and many other applications. There are a couple of notations before we go into the example. The first notation is about the direct cost of neighbors. So C of X and Y means the cost of going from X to Y, which is in this example is 4. Now, if two nodes don't share a direct edge, they don't have a common link, for example, X and Z, the cost between them is set to infinity. It doesn't mean that we cannot reach Z, it just means we don't have a direct link. The second notation is the D notation or the distance notation. So the D notation, for example, for source S to reach a node V is called dV subscript S or just dV. And then let's say an example is 10. So what does that mean? That means within the node S currently it believes in order to reach V through some route, we don't know which route yet, it will cost it 10. The third notation is the P notation. P, for example, as X wants to reach Z, and there is a intermediate here, intermediate node, let's denote it as U. So in this case, from X perspective, reaching Z needs to go through U, and that would be the previous of Z is equal to U. So U is a node, so what we're saying, in order to reach Z, I have to pass my traffic through U. Perhaps the best way to understand the Dijkstra's algorithm is to go through a worked example. So what we have here is a network composed of 6 nodes. So note here that the nodes can be denoted as numbers or could be denoted as letters. What we are going to do is we're going to go through the Dijkstra's algorithm. We have 6 steps. This is the maximum number of steps that the algorithm will go through, which is equal to the number of nodes. So we have here 6 nodes, so the maximum number of steps would be 6. Now, to run the algorithm, you have to have a starting point, and in this example, we are given that U is our starting point. So we are starting from here, and what do you want to do? You want to calculate the shortest path to all other nodes in the network. So the first step, I am at U, and I have no idea what's happening in the network. I'm connected only to X, W, and V. So, and I know the weights or the costs to reach these nodes. So what I'm going to do here, I'm going to write the distance. So d is the distance to this node, the distance to node v, which I know is 7. And how to reach it? Well, it's just through it directly. So I'm going to reach it directly through u, because I'm at u. In order to reach v, I just go to it directly. This is what means p. P is the previous node, and 7 is the current distance to that node. Let's look at the second node. So w, the distance to w is 3. So I'm going to put 3. And how to reach it? Well, directly. And then the third node, x, has a weight 5. And how to reach it? Directly. Now, let's look at y and z. Now, I don't know how to reach them yet. So what I'm going to do, I'm going to put an infinity here, meaning I don't know how to reach them. And I don't know how to reach z. Just to let you know, so n prime is the list of nodes that I'm sure how to reach. Okay, and then you see here, I don't know how to reach any other node. I only know how to reach the node itself. So what I'm going to do here, this is the magic step. You're going to look at these numbers, these costs, and you're going to pick up the shortest, the lowest cost. So the lowest cost here clearly is 3, and it's going through the point itself. So why is that? If you look at this, why did I pick up this and I'm now sure that this is the shortest path? So this is basically here the shortest path to W. Now why is that? Because why didn't I pick up V, for example? Well, imagine there is a connection between W and V, which there is, and this connection total connection will cost me less than going directly to V. And you can see here clearly in this example, if I go to V through W, it will cost me less than if I go to V directly. So I'm not yet sure, I don't know about this number yet, but I'm not yet sure if reaching V directly would be useful or not. But what I'm 100% sure that I cannot reach W in a cheaper cost than going to it directly. Because if I go here, I have to pay 7 plus something else. If I go through here, I need to pay 5 plus something else, which I don't know how much is something else yet. So what I'm 100% sure is going to W directly is the minimum cost. So what I'm going to do, I'm going to add W to the known nodes. I know how to reach W and I reach it directly. Directly mean the previous node is U. Alright, so since W now is in the club, I'm going to go to W and try to reach other nodes from W and see if the cost is changing. So let's try first V. If I'm trying to reach V through W, the total cost would be 6, alright, which is better than 7. So I'm going to update my cost to 6 and I can reach V through W. This is a better path. So that's a good thing. Now I don't need to worry about W here because I already found the shortest path. Let's see X. If I'm trying to reach X through W, it will cost me 3 plus 4, which is 7, which is higher than 5. So I didn't really find a better path. So what I'm going to do, I'm going to just take the old path and just keep it. Let's see Y. Well, I can now access Y. It was infinity before, I didn't know how to access it, but now I can access it and it will cost me 3 plus 8. And how do I access it? I access it through W. How about Z? Well, Z, I don't know how to reach it yet, so I'm gonna just put infinity because it's not yet known. Now looking at this row, do we have a winner here? Well, yes, we do have a winner, is this one. That means I can reach now, I know how to reach X, this is the shortest possible path to X, and it's just going directly to that node. So from U directly to X. So but what's the difference here between this and previous line? Now I'm 100% sure that reaching X directly is the shortest path. So what I'm going to do is I'm going to add X to the known nodes list. Alright, welcome X to the club. Now what do we need to do is we search from X. This is a new node and we know how to reach it with the minimum cost. We know that reaching it directly is the minimum possible cost. So what I'm going to do is I'm going to try to search for reachability to other nodes. All right, so let's find if I'm trying to reach v through x. This will cost me infinity because there is no direct connection. So basically, there is no update. I'm going to use the previous known link, which is 6w. Just put it down. And how this one, I already know how to reach it. I know how to reach x. Let's look at y. If I'm trying to reach y through x, how much this will cost? Well, obviously, this will be 5 plus 7, which is 12, which is higher than 11. It's not really a good path, so I'm going to use the old path that I know. How about reaching z? Well, there is a new path now, and this path will cost me 5 plus 9, which is 14. I know how to reach it, and I need to reach it through x. Okay, all right, because 14 is less than infinity, that's why I put it into the list. Now let's look at this row. Do we have a winner? Yes, I do have a winner, which is 6w. Now I'm sure that going to node v through w is the shortest path. So I'm going to add this to the known nodes. So I know how to reach u itself, I know how to reach w, I know how to reach x, and now I know how to reach the point v. All right, so now I have v in the club. Now I need to try to reach things, and how to reach v is through w for the shortest path. I'm now going to try to reach other nodes from v. So how does that work? Well, I don't need to worry about v, not about w, not about x. Let's try y and z. We haven't yet had red circles on these. So let's try first y. If I'm trying to reach y through v, how much the total cost would be? This is the path. It will be 3 plus 3 plus 3, which is 9, which is better than 11. So I'm going to have a new path here, which is 9, and the previous node is v. All right, how about trying to reach z? Well, I can't really reach it from v, so I'm going to just use the previous known path. And now what I'm going to do is look at the row. Do we have a winner? Yes, there is a winner here, which is 9v. And now I know how to reach y. It will cost me 9 to reach it, and I can reach it through the point v. So y is now in the club of known nodes. So we'll have u, w, x, v, and y. All right, so we know how to reach y. Let's try to reach things from y. Well, obviously I can reach z from y. I don't need to worry about all of these, already done. V, y, w, x, y. Now I need to check z. I'm not yet sure how to reach it. If I'm trying to reach z from y, it will cost me anything I need to pay to reach to y, which is 9 plus 2. All right, so 9 plus 2, this would be 11. And how do I reach it? 11 is less than 14, so obviously I'm going to add it. And how to reach it is to reach it through y. Okay, so there is nothing to compete with, so this is surely the best path towards the point z. Now I know z, how to reach that, so I have everything is set. There's no any more iterations. I'm just going to add z to the known list. So now I know how to reach all the nodes in the network. So now you might ask, all right, so, okay, how do, for example, how can I reach point, just give me a random point, y. So for reaching point y, you need to go to the table, check here the table, go to the optimum link, and you say, well, in order to reach y, let's put this as an example here. In order to reach y, you have to come through v. So v will lead you to y. Okay, then you ask this question. I'm not looking at this graph. Okay, don't look at this, just on the table. And then the question is, how do I reach v? Well, let's go here. In order to reach v, I need to go through w. So you just put here w. All right, how do I reach w? Well, let's go here. No, okay, so just reaching w, you just go directly from u to w. So from the table, you can now put the optimum path. You can actually draw this if you want. So reaching y would be through v, through w, through u. That's the shortest path towards y. and so on. So if you want to draw the shortest path towards any node, it's very easy to do that from the table. Now a couple of notes here. So one note is that you need to have the starting point in order to draw the Dijkstra's algorithm. So if you're starting from X, you would have a different steps. The other note is that the number of steps is not necessarily equal to the number of nodes. It could be less. In the previous example, we have seen an implementation of the Dijkstra's algorithm, but what you see here is the formal introduction of the Dijkstra. It's written in a pseudocode method. So at the first step, and then we called it step 0 in the example, what we are doing, we are taking the node U. So remember, our source is U, and this is the only node that we know how to reach it. So we initialize the n prime list as only having a node U. Remember, n prime is the set of nodes whose least cost path is definitely known. The next step is we take all the nodes connected to U and update the cost or the distance to these nodes with the cost of the edge. So remember, we had here X and Y, and we have different nodes. If we know the cost to them, then we update the D value. If they are not connected, there is no edge, we are setting an infinity to the D value. So this was the first step. So then what we have done, we repeated the algorithm with the same number of nodes inside the network, and we iteratively added these nodes. So in the loop, what we have done, we pick up W, which is not yet in the n prime. So W belongs to n, but is not yet in n prime. So what we do, if we found the DW is a minimum, if you find that there is a minimum towards that, we add it to the n prime list. After we did that, we check all the neighbors of, or the nodes neighbors of W, and let's call them now V, and try to reach these neighbors via V. So let's just write this, draw it here. So this is W. We just found a new D for this W, and then we are having different nodes. Let's say this is a node V. So now we know how to reach W, and the reaching it will cost us DW. My reaching V is DV, and what you are asking here, the question is, if I use W to reach V, this will cost me DW plus the cost of this connection, which is CWV. So what you're asking, is reaching V via W less than reaching V directly? If it is less, then you will take this as the new minimum. If it is not, we just keep the old value as it is. And so on. You keep running this algorithm until all the nodes are inside the known nodes list. The distance vector algorithm, on the other hand, are algorithms that do not have full knowledge of the network. They are distributed, and thus it's lighter to use in very large networks. So what happened here is that each node waits for a change in the local link or a message from its neighbors. So what it happened is in the routing table, it recompute its estimate, recalculate the estimates for the routes to other nodes, and then if there is an update, it will notify its immediate neighbors. So if the immediate neighbors found that this update is necessary to propagate further, they will also do this notification for further nodes. But if it is not necessary, they will keep this information to themselves. Now, I've chosen not to go into much depth of this algorithm. It's not very complicated, but it's outside the scope of this course. The topic of routing is quite deep. We just scratched the surface on the theory of two most important classes, which were the link state and the distance vector algorithms. However, implementing the link state or the distance vector into a practical algorithm is a different story. In a practical algorithm, you have to design the messages, you have to design all different aspects related to the implementation as well, including the theory of the routing. These are a few of the famous and very important algorithms. So we were going to use the RIP in the lab. So it's Routing Information Protocol. So it's usually used for small networks. OSPF is also very famous and is an open source. So open shortest path. So the word open, it's a known algorithm. It's not a proprietary for any vendor. Now there are some algorithms which are proprietary. For example, the EIGRP is Cisco proprietary. So what you'll find that it might not be compatible with routers that are not Cisco. On the other hand, the BGP perhaps is the most important. This is used to route the traffic in the actual internet routers. This is a quite complicated algorithm. In fact, there are books about this and it takes people a few years to understand it. So these are some of the information related to the RIP. So this is a very easy to implement algorithm. You can set the distance metric for different links for the number of hops, and you have a maximum up to 15 hop. The second algorithm is the OSPF, which uses the link state packet for disseminating the information. So the topology is calculated using Dijkstra's algorithm, similar to the example we saw in the previous slides. So advertisement of new links are sent to the entire network. There is a closely related algorithm called the ISIS. This is widely used in telecom operators such as Telstra, Vodafone, and Optus, but this is a layer 2 actually algorithm. So it actually routes the frames in their layer 2. We're not having more details about it. So people working in networking might not be familiar with this, but people working in the telcos, they are quite familiar with this algorithm. BGP perhaps is the most important routing algorithm and is used for the internet. So it's what really makes the internet works. Now you need to understand that the internet is a collection of autonomous systems. An autonomous system is a collection of routers that belongs to a certain administration, for example, to a certain telco or an internet service provider. So if you have a collection of autonomous systems, so each autonomous system has thousands of routers, and these autonomous systems constitute the internet. So BGP has two main branches. So you have the eBGP or the external BGP. It defines the interface between autonomous systems, while the iBGP, it defines how to propagate the reachability within the routers of the autonomous system itself.